Hi there and welcome back everyone. This is the first video of the DB2 course chapter 10. Okay, so we've spent lots of time looking at the internals and the inners of different types of indexes, of the B plus trees and the order indexes and the cracker indexes in the database systems that we are discussing in this course. Now it's time for a chapter in which we marry the presence of indexes and the performant evaluation of queries. Indexes are in itself are really an object worth of study, but of course their real value is in supporting particular queries in our system. And well, only if the queries and the indexes match, if the indexes really can support us in query evaluation, then some real value is to be had here. And that's exactly what we are trying to cover in this chapter. It's matching queries and indexes. I think, if I'm not mistaken, this will be a PostgreSQL only chapter. All right, so we will largely talk about B plus trees here, but about new kinds of indexes based on B plus trees also. So there is something to be learned here. After this chapter, we should have a real good grasp on and a good feeling of what indexes can actually help a particular query if it's just too slow. All right, so let's see what we find here in the discussion. Okay, so only the mere presence of an index. So I've got an index I now on some column T, or on some table T, and it's column A. The presence of this index does not guarantee that the queries on this table will actually be sped up. There has to be a good match between the query and the index. Will the index really be helpful in reducing query evaluation cost? And will it reduce the evaluation cost in a significant fashion so that the effort of accessing the index is really worth it? This is actually the last point on this particular slide. Even if an index appears to match a particular predicate, a search predicate in a query, for example, we still have to recall that accessing the index I itself will cause I/O. We have to access the root page, then the child page, then the leaf pages, the sequence set of leaf pages of an index. We have to perform lookups from that sequence set into the heap file. This can cause random I/O if you're not careful. We have talked about all of these aspects already. And the question is, the index may match, but will it actually save stuff? Will it actually save us from effort that that sequential scan would have anyway? So is there really something to be gained? This is one of the questions here. All right, then there's of course the basic questions. Hey, here's a predicate, search predicate P in a query, a where predicate, for example, could be a having predicate too, could be a filtered aggregate too. So there's lots of places where such predicates play a role in SQL query evaluation. Are the columns that are mentioned in the predicate, are they even present in the index I? If they aren't present, then there is no point in using index I. Index I would be useful for many queries, but not for this particular query and its predicate P if the columns are not matching. There's other considerations. The match between a query and an index might be so well that all columns, really all columns mentioned in the query, not only those in the where predicates, but maybe also even those mentioned in the select clause of a query, are all columns referenced by a query present in an index. This could be super interesting because then no other columns would be need to be looked up in the heap file of the table. Sounds like query evaluation could be performed with using the information that is present in the index exclusively. That would be really awesome, and we will find use cases for that, and we have some considerations and discussions and remarks to make there. Okay, and then of course the indexes that we have talked about, the B plus tree index, but also the order index in MongoDB, but we are focusing on B plus trees here. These have been ordered indexes. when we scan the sequence set of such a B plus tree, we encounter the rows of the underlying table in a particular order. That might be the order that a SQL order by clause or maybe a group by clause is requiring. And that could be really useful, and it could really save a lot of sorting time if just scanning the index will produce the rows in an order that has been requested by, say, an order by clause. So we could order the rows in a table without ever using a sort algorithm. That would be also quite interesting. So lots of considerations, lots of interesting aspects and angles of index technology and their marriage with queries. And this is exactly the topic of this particular chapter. Okay, first things. Indexes on expressions. Okay. All right. So first, let's recall the playground table that we have always been working with. It's the indexed table. All right. And the index table had 3 columns. One of these columns, the A column, is a primary key, and we know that the system by default will erect a B plus tree over that particular column A. This is this index that I've also marked with this nifty key symbol. Okay, so that would be the primary key index. But as you can see, there's also a second index here, the indexed underscore C index, which I've built over the numeric column C here. Okay, so 2 B tree indexes over this index table. Okay, right. So we would hope that many queries would be supported by the presence of these 2 B tree indexes. Maintaining these B tree indexes is not cost-free, so we really hope that we get some reward for all the effort here. And one hope could be that the following query is indeed supported by these 2 indexes. Okay, so that's a query over the indexed table, all right, and here's a where predicate, and the where predicate mentions the column C. Okay, so if any of these indexes could be of use here in this situation, well, it's probably the indexed underscore C index, because well, it mentions the C column over which we've built that particular index. All right. So this is just some simple arithmetic expression over I.C, and then a comparison. Maybe this could work as an index search condition. Let's switch over to PostgreSQL and find out. All right, so here we go. Well, what you see is the playground table setup, table indexed, and the definition of the 2 indexes. As you remember probably, we get hold of the indexed underscore A index by just renaming the primary key index that has been created by PostgreSQL anyway. So we've got both indexes in place here. Then we fill in the 1 million rows that we've filled in so many times already. We give the system some time to think and consider all the indexes, make itself aware of the order of rows in these indexes, and so on. All right, so we have done all that. Let me show you the current state of the table and the indexes. Yeah, looks good to me. There's the 2 indexes that we expected. All right. So here's the query from the slide. It's featuring that particular predicate on column I.C, all right. So maybe this is a job for index underscore C here, and that simple comparison with the 90 degrees value. Okay, so let's go. And no index support. No index support. Indeed, we are performing a sequential scan. Well, that sequential scan will finally output column A, all right, so I can see that. But it will evaluate. It will evaluate this arithmetic expression and the comparison here using the normal expression, interpreted expression evaluation that we've discussed in previous videos. No index support at all. It appears the index indexed underscore C does not match this particular predicate. Indeed, this particular index has been built to support comparisons or predicates that look like this. Hey, column C, is your value the value V? That's something I can easily support with a B plus tree. Or is your value greater than C, or maybe V, or maybe greater than V but less than W? This is the type of queries and the type of predicates that such a B plus tree over the C column is supposed to support. All right. And it can only support these particular predicates because the relation of these predicates, of course, depend on the order of C column values. But here we are not interested in the C column values, but well, in some arithmetic or trigonometric transformation of these values here. The arccosine value of IC and then converted from radians to degrees here. Well, this is not the I dot C value. The sort order of these values would be completely different than the sort order on the C column alone. All right, so no index support here. Well, maybe we can repair the situation because we know something about these functions degrees and arcsin that are used here in the web predicate. Well, we could, for example, use this equivalence here. We could, in a sense, remove the degrees here on the left-hand side. You see, we go from degrees x to x here on the left-hand side. If we also convert the right-hand side of the comparison, we go from y here to this expression that performs the conversion from degrees to radians. Okay, so we could do that. We could do that and then get rid of the degrees here at the cost of complicating the right-hand side. So then we would be left with this particular expression, and well, we could use this second observation here to get rid of the arcsine 2, the inverse of the scene. We could just apply this transformation here, and then well, then after this transformation the x is completely isolated here, or in this case the I dot C would be completely isolated. Okay, we would end up with the comparison that would look like this. Well, I dot C is equal, I dot C completely isolated, well, is equal to some expression that we have then constructed. This looks better to me, I would say. All right, so let's try that. And indeed, I've tried that in this query below. So these two transformations, I had them applied to the comparison expression that we had in the original query. Now I dot C is isolated. And well, the right hand side is an expression now, but it's looking more complicated. But well, let's see. It looks complicated, but it based on literals and another literal, and this is literal 2 in disguise. It's the 3.14 that we all know and love. Okay, so this should actually be a literal expression. It could be evaluated at query compile time. Let's see what goes on there. All right, so well, some of the magic has indeed happened. You see that, well, this is indeed a comparison with I.C now. So I.C has been isolated. And indeed, the right-hand side expression has been simplified quite significantly simplified to just a single literal of type double. The literal 1 of type double. But still we are looking at a sequential scan here. The indexed underscore C still hasn't been used, and the course for this is indeed this this cast here, right? So this is a predicate not over I.C but over the casting of I.C to a double. Okay. All right, so we could even get rid of this particular casting if we perform the casting ourselves inside the query. All right, so that's what I've done here. I've converted the right-hand side explicitly to this numeric 3,2. So that would be a 1 with two zeros behind the decimal point after all the compile time simplification of the expression should have been performed. And this is a numeric 3,2 value that should be immediately comparable to the I.C column without any further casting on I.C going on. This should do it. All right, so let's see. Indeed. Indeed. So now the index condition is simple enough. The I.C has been isolated, no casting applied, no nothing. On the right hand side we see the expected 1.00. This is an index condition that is indeed workable for an index scan. In this case it's an bitmap index scan, because we can expect that the table index is not ordered on its I.C column. And well, we have talked about the scanning and the access of non-clustered indexes in the previous chapter. All right, but we are indeed using the index scan now. Okay, so we really only had to be careful to isolate this particular expression here on the left-hand side. So this has been quite the transformation of the predicate, but well, has it been worth it? And I think so, yes. So let's just repeat these two queries. The original query, written with the predicate in its original form. Sadly, no index support. This will be a sequential scan in the background. Let's see what we find as execution time here. Okay, so 1.7 seconds for this particular query. All right, and now the rewritten form. The rewritten form with I.C isolated, no casting, no nothing involved. This will lead to an index scan, a bitmap index scan. Oh wow, all right. So execution time went down from, well, 1.7 seconds to 70 milliseconds. That's quite the improvement, I would say. So, well, yeah, applying index technology to queries with such complicated predicates, with such complicated arithmetic expressions or expressions in general in predicates, still is worth it. But this transformation, the transformation has been rather painful, and this has been a one-off thing, right? So we were building on some insight into the involved expressions regarding these two transformations here, and so there was some manual labor involved here. All right. So modern database systems have an answer to that, and that's called indexes on expressions. All right. So let's see. The problem that we were facing is in a more general form would be the following. We are performing this particular query. There is a column I.C involved in a complex expression, and that complex expression is actually a gray or black box for the optimizer, because we were equipped with the knowledge of how we can transform the sign, the A sign, and how we can get rid of the degrees function. Because of this knowledge, we were able to remove this gray box and actually perform or compute its inverse. So we were applying the inverse of this gray box to the left-hand side and to the right-hand side. As a consequence, the left-hand side is now isolated and we are left with the index column. That's good. And the right-hand side has become more complicated in general. All right, that's the price we are going to pay. Maybe the right-hand side can be evaluated at compile time already. But this would remove the black box. But all of this is based on the insights and knowledge about the functions inside the gray box. And the query optimizer in general does not have this insight. Query optimizers do not know about sophisticated algebraic equivalences or properties of the functions that are involved in building complex expressions over this column I.C. So indeed, this may be complex, and maybe it's even consisting of user-defined functions about which the query optimizer just has no knowledge. Maybe it's not even possible at all to find this inverse here, because the function that is defined by the gray box is not bijective. Then this approach is just a no-go. Okay. And one answer to this challenge is the so-called expression-based, or sometimes called function-based indexes. These are very peculiar, very specific indexes that have been built to support queries, to support predicates that are built using complex expressions over the columns of the index table. All right, so we are not indexing the column values in that table T. We are indexing the value of expressions over these column values, over some or one column value or many column values of the table T. And the create index statement then indeed mentions this particular expression. So you see, this is just a normal create index statement. We have seen that before. We will still build a B+ tree index, but the values that are being used to build that particular B+ tree index, the values being held in the leaves, the values being placed in the separators of this B+ tree will be the values of this expression E. This is expression or function over the columns of table T. When we insert rows into such an expression-based index, then the expression E will be evaluated for this particular row to be inserted. This expression will yield a value, and based on this value we will place the row inside the index. Okay, so this expression E is evaluated at row insertion or row update time. This is very important. Okay, so already when the row is inserted, we evaluate E, some value is being computed. This is the search criterion. Under this particular expression value, the row will be inserted in this expression-based index, which can be very nice because then all the effort of evaluating the expression E is just relegated to row insertion time. If our table is inserted into or updated very infrequently, that's cool. If it's queried much more often than it's being updated our table, then we don't have to invest the time in evaluation of the predicate E at query evaluation time. We can relegate that to the index insertion time. All right. So this, as I told you, this is a very specific index. It has been built to really support this type of predicate. The expression, the exact expression E on the left-hand side, and then some comparison operator, probably something that can build a range query. So equals comparison or greater equals comparison or so on, and so on, with some literal or with some value V. All right, so from these two components, from this comparison operator and the value V, we will build an index condition. Of course, the entire index internally will not be organized by the column values of T. It will be ordered by the expression values that we have computed, of course. There's a nice trick there that we can play because there is a keyword in the creation of index structures that we have not used that far, and that's the create unique index keyword. So this restriction on indexes says that no two rows may be inserted whose value on the indexing criterion is equal. Okay. Now that if we use this create unique index, this unique index modifier in the creation of such an expression-based index, we can make sure that no two rows inserted into table T will have the same value when we evaluate the expression E over these two rows. Okay, so this can be used to do some nice constraint and restriction logic already at row insertion time. So we can use or abuse the index to perform constraint checks that protect us from two rows being inserted that have the same value under expression E. Lots of stuff that can be done there, but this is not the focus of this particular discussion. Okay. I think we should explore how PostgreSQL fares with these expression-based indexes. Okay, let's see. So back in the terminal here. All right, so what we would do now, if the query that we were looking at, this particular query, if this is a query that is really prominent in our workload, that really defines our workload, defines the speed of our applications, and we can expect this query to be fired and evaluated like multiple times a second or really often, then it might be worth to consider the creation of an expression-based index just for this particular expression. And you see, this is just what I'm doing here. This is not an index over the column C, it's an index over this expression over column C. All right, so let's create this particular index. All right, analyze, all right, done. Okay, so let's check the state of the table and all its indexes now. All right, so there are indeed 3 indexes now. 3 indexes, and this is the expression-based index. Indeed, it has been created over this expression over the column C. Okay, so this will be an expert to answer queries that use search predicates that use this exact expression here. You see, even the cast has been baked into the expression, the cast. So super specific, but probably super useful for queries that use these types of predicates. Okay, and well, now we could just write our applications or ad hoc user queries in the fashion that we were aiming for in the very beginning. We would just use this particular expression here, and well, we would hope for index support. So let's see what happens. Oh, that went quick. Okay, so yes, indeed, index support has been used, and as you can see, the index condition is indeed this complex expression, but it perfectly fits the order of the entries in the sequence set of the index tag as in C index. Perfect. So this is expression-based indexes. There's other use cases for such expression-based indexes. Some that you may find out there used in practice frequently is, for example, an index over textual columns like this last name column in my table. But I would store the last name inside my table, but I would build an index over the lowercase version or variant of these last names. All right, so that would be a very specific index, a lowercase index that would be used in queries like this. So you will find such queries often in applications that have to cope with user input that normally shows some inconsistent upper and lowercase characters in there. So maybe somebody has maybe somebody named Obi-Wan has provided this as his last name. Then no worries, we would just normalize the search input here, and well, we would also normalize all the stored last names in our table so that we can make sure to find this particular user and its record. And such normalization could also already be baked into the index computation here. Okay, so this is something that you will find out there. Sometimes you can build indexes over multiple such columns. So we could, for example, build an index over the concatenation of the first and the last name. Sometimes this concatenation will be the search criterion. We could build a B+ tree over this concatenation, maybe even with an intervening space here, to support queries that look for such full name specifications inside our underlying table. All right, so can turn out to be quite useful here. Okay, so that's indexes on expressions or expression-based indexes, if you will. One last point here. Let's switch back to the slides, and one caveat in a sense. All right, so let's consider a different example for a change. So let's put table index at the site, and let's look at a different table. Let's look at a table of people. Table of people here. All right, and people are stored with their name and with their birth date. Okay, all right. And my application will search for people, based on their current age. Okay, and the current age can of course be computed very easily if I got the birth date information. All right. So I will probably see queries like this, queries with predicates like this. So given the birth date of person P, compute its current age in years, and then perform some comparison here. So we are looking for the adults here. All right. So getAge is the function, a UDF, that I can easily define. You even see the definition of this single line function on the slide here. Okay. So that's the getAge function. You specify a date of birth. I will return the age in years as an integer for this particular person. It's very easily done. I would just use the now function. Okay, this is a built-in function into PostgreSQL that returns the current system time. So when I evaluate this particular function, now will be invoked. Now we'll perform a lookup at system time and return the current system time as of this particular invocation time of the function. All right. I would then use this built-in age function. Actually, it's built inside, built into PostgreSQL, and perform the required difference internally from the current system time with the specified date of birth. Okay, from that I would just extract the years, also some built-in functionality into PostgreSQL, convert that into an integer, and I'm done. All right, so that would be the type of query that I can expect. And because I can expect these types of queries every few milliseconds in my applications, I will build a very specific index, an expression-based index to support these predicates. So I'm not indexing the birth date column here. I'm indexing its return value under the getAge function. Okay, so that's my clever plan here. So how do we expect the RDBMS to behave? Well, of course, I hope that the DBMS will use our cool people age index, our expression-based people age index. Why wouldn't it? So let's switch over to the system here, to the terminal again. Let's clean up the terminal output here. Okay. And then look at this particular example. I brought it with me here. So I will first define this getAge function, the function that we've just seen on the slide, defined. Okay. Then I will drop a table people. Maybe there's already one. I will create it anew and then build my expression-based index. And well, this warning sign already says that something may be fishy here. All right. So let's see. I don't think why should this oh, it's not working. It's not working. I get an error message that says functions in index expression. Okay, this is the function in the index expression here, the getAge function. Functions in index expression must be marked immutable. Okay, okay. So immutable functions are special functions inside PostgreSQL that are known to behave right like true mathematical functions, whose value is only dependent on the function parameters. Okay, so that's true mathematical functions whose value only depend on the arguments that I'm supplying to this particular function call, nothing else. This getAge function is not an immutable function. Actually, such special indicators that the function is immutable could be added here. But I'd better not do that, because this is indeed not an immutable function. This function is referring to the current system time, and invoking this particular function now on a specific date of birth and invoking it on the same date of birth at some time in the future might yield different age values being returned. Okay. So this is not a true function in the mathematical sense. In particular, this function this function might return one value when we insert a row into an index at a particular point in time, and it might yield a completely different value when we perform a query over these rows, because then the get8 function would consider the now value at query time, not at index or row insertion time. And to forego the semantic problems, PostgreSQL forbids the creation of expression-based indexes on non-immutable or immutable functions, in a sense. All right, so if I would be very explicit here, then I would mark this particular function as being volatile. So it's dependent on the system environment, in this case, the current system time. Such functions may not be used in expression-based indexes for obvious reasons now, I hope. I hope they're obvious to you now. All right, so nice plan, not to be implemented in the fashion that we've just outlined. So be aware of that, and the system is aware of that, that expression-based indexes have to compare values at index creation or row insertion time and query evaluation time. These two evaluations of the expression must fit together. If they do, then there is really some significant advantage to be had. All right, so that's it for expression-based indexes. Much more to be added to our discussion of indexes. I hope you will be around by then. See you soon.